Hello, and in part 5 we're going to move away from capacitors and have a think about inductors. First circuit to look at, this one. An inductor that we're going to connect across a voltage source of a constant voltage when we close the switch. What happens? Well, key important formula for an inductor. The voltage across an inductor, which I've called E here, it's a function of time now, is equal to L, the value of the inductance, times di dt, the rate of change of current through the inductor. And the current is now going to be a function of time as well. In this particular case, though, the voltage across the inductor isn't a function of time. It's constant. It's fixed to the value of Vc, this voltage source here, that's placed directly across it. So I could write Vc equals L di dt. In other words, di dt is just equal to the constant Vc over L. That's a constant, which means that the rate of change of current is constant. The current at time t equals 0, when the switch is closed, is 0. We know that because you cannot suddenly change the current through an inductor. The current through the inductor before the switch was closed was 0. There was no circuit. No current could flow. Therefore, the current through the inductor just after the switch is closed must be 0 as well. So we have a current which is 0 at time t equals 0, and then has a linear gradient. The rate of change of the current is constant. It's almost not worth doing the integral to produce the answer. The answer is just going to be equal to this. Plot that on a graph, and we would get the current against the time would just look like this. It will be 0 until time t equals 0, at which point it would just head up in a straight line with a gradient of Vc over L. It's just as simple a case to analyse as the capacitor with the constant current source flowing into it. A more interesting and a more common problem is what happens if you're charging up an inductor slowly by feeding it from a voltage source through a resistor. That's this case here. Now what? Well, we can start to apply all our usual circuit analysis techniques. The voltage across the inductor I've labelled E. It's a function of time, and this time it really is a function of time. It's going to be changing. We have a resistor here. Now the voltage across the resistor is going to be V0 minus E. V0 on this side, E on this side. Therefore, the current flowing through the resistor, given by Ohm's law, is given by this formula here. The current through the resistor, which is a function of time, so I'll label it I, function of time, is V0 minus E over R, the value of that resistor. We also know that for an inductor, the voltage across it is given by L times the rate of change of the current. So E, function of time, is also equal to L times the rate of change of current. How do we start to analyse this? Well, we'd like to eliminate the current from these two simultaneous equations. And to do that, we either have to integrate this one or differentiate this one. Differentiation is easier than integration, so let's differentiate this one. We'll notice that I could write this as I, the current, equals V0 over R minus E of t over R. This is a constant. So if I differentiate each of these terms with respect to time, this is not changing with respect to time. That's just going to disappear. Going to end up with di dt equals just minus 1 over r times dE dt. And now I can substitute this into here and get E of t equals minus L over R times dE dt. It's probably beginning to look familiar. It's the same type of equation that we got when we were analysing the capacitors. And I can solve it in the same way. Write this as minus dt over, in this case, L over R equals dE over E of t. And that's now ready for integration. And I want to integrate from, right, well, from time t equals 0 up to a time of interest t. At time t equals 0, the voltage across the inductor is equal to V0. And I know that because there's no current flowing through the inductor just after the switch is closed, because there was no current flowing through it just before the switch was closed. If there's no current flowing through the inductor, then there's no current flowing through the resistor. If there's no current flowing through the resistor, there's no voltage drop across it, so the voltage on this side must be equal to the voltage on this side, and that's just V0. So, at time t equals 0, the voltage E is equal to V0. And at some time t, the voltage will be, I'll call it V of t now, the voltage across the inductor at the time of interest t. I can now integrate that up, and that will give me minus t over L over R on this side, and the log of E of t evaluated at V of t and V0, and that's just the log of V of t over V0, using those results that we saw before. Take the antilog of both sides and multiply up by V0, and we end up with V of t, the voltage across the inductor, is equal to V0 times e to the power of minus t over L over R. And you can see that once more this is in the form of an initial value times e to the power of minus t over a time constant. But here the time constant is L over R. For a capacitor, the time constant was R times C. When you have an inductor and a resistor in a circuit like this, the time constant is L over R. This looks like this in a graph. The voltage starts off as at V0, as we're expecting. When t equals 0, this is just e to the power of 0, which is 1, so it evaluates to V0. And then as time increases, the value of this term here starts to decay down to 0, and the voltage across the inductor decays with it. Just like with a capacitor, after one time constant, you're down to 36.8% of where you started. That's all we need to know about inductors for the moment. Next time, we'll have a look at the shape of those graphs in a bit more detail and come up with a few useful rules of thumb to know about.